Actually, when I record Zoom, I can record like my whole screen or just when I'm like the Zoom call and everything? Sharing half my screen. Okay. Here's another one. So this is a video of, which there's music, I think, yeah. Just our robot. When we migrated from our gazebo to this new simulation software called Weebots. And here it autonomously detects that it's fallen over and tries to get up in its own way.
Mm-hmm. We do have a lot of simulation work for the software side, just because it's much easier to implement and test it out versus, actually running the robots. Yeah.
So this is called RViz. It's robot visualization of all the sensor data. So if you could see here, can you see my mouse?
I can see it. Yeah.
Okay. Yeah, you can see here, this is original. Okay, I got rid of it. But that was the original image. Yeah, this is the original image, for the webcam, and then this is through like OpenCV augmentation, what we get. And essentially what we do is we extract all the white lines and we make those into points. We take these points, this is what's printing out here. We're not orientated properly, so it's not lined up. And then we use these points as reference for our localization algorithm, which generates these dots, these green dots, where each one represents a probability of where our robot can possibly be. So this was a older model, but essentially works the same. Our newer version actually localizes much faster. Okay. Is 610. Is there a chat? I'm trying to figure out how to do this chat stuff. Eric, if you can monitor the chat, because I don't know how to open it.
Oh, sure. There's the chat.
Oh, I see. Okay. So yeah. I guess we start with the presentation.
Yeah.
Do you see the full presentation?
Yeah, I can see it. Yeah.
Okay.
All right. I guess I'll start. I guess hello everyone. Welcome to our kickoff or the Ultra RoboSoccer teams. And yeah, and then next slide, please. So I guess just to introduce ourselves, we have here Jonathan. Say hi,
Hello.
Jonathan.
Yeah.
Yeah. And I'm Eric. So we're both fourth year Insign Robo Options. We are the project manager for the team. Jonathan's also the software lead. I'm also the beta lead. We also have Hamya. Sorry, I don't know how to pronounce the name properly. So she will be our new mech lead. And we also have Jeff Ma as our electrical lead. Shayar, Jason, and Nam will be our advisor this year. They haven't graduated, but they'll still be on the team. Next slide, please. Yeah, so these are just the photos of our team designing, building, and testing our robots. So yeah, I know most of us has been, I guess, studying or working online, so rarely get a chance to see each other. So this is just to get you guys give you guys the feel of how we work together. And yeah, you can see everyone coming together here and trying to, achieve the common goal, which is building a working robot for playing soccer. Yeah. And then next slide, please.
Okay.
Yeah. Then just more photo of us doing like workshops and that sort of stuff. Yeah. And next one. Yeah. Yes, sir, I was gonna say.
No.
Oh, okay. I guess I'll go through briefly about our visions and outreach of the club. So for us, we heavily relies on mentorship and learning from each other to transfer the knowledge of advanced robotics in this case. We also maintain a very diverse background, ranging from different disciplinaries as well as different years. We have like a bunch of first year students last year that have actively contributed to the project, as well as even like fourth year students like us, or like even alumni that's currently working in industries still on the team, and introducing new concept to all the new students. So it's a really great environment for us to foster the next generation of robotics engineering in this case. Next one. So this is just a video of our current robot, Bez. I think we show part of it in the user general kickoff. Yeah. Yeah, so this is just show the robot walking, like it's a walking behavior. As you can see, it's trying to balance itself so it doesn't fall over. Yeah. Yeah, and this is the get up. I think Jonathan already showed it in the simulations. This is how it looks like in real life. Yeah. Yeah, it was kind of important because robot kind of fall over a few times in the competition. That's quite normal. So have a good get up that's fast and efficient is important. Just doing a get up with a backflip, kind of fancy. Yeah. And just it's walking behavior and go to the kick. And fall over. Yeah.
Yeah, this is.
Yeah, go ahead.
Yeah, so this is the similar situations. You can see real-time ball localization. As we move it, the ball location changes with reference to us, and it's very fast. Like that was all real time. So.
This is some of the balancing stuff that we did previously. Try to keep yourself balanced. And it just sounds random dancing. Yeah.
No, I don't want to do that.
Yeah.
Do I? Oh no. Oh, that's how I did that. Okay. So it's my turn. Okay, so first of all, RoboSoccer and RoboCup. So we go and participate at a competition, an international robotics competition that was started in 1997 called RoboCup. Very original. With the very simple goal of building a team of humanoid robots that can beat the 2050 FIFA World Cup champion team. Very reasonable. Very, we'll get there. Yeah. So and the competition has resulted in advancements in numerous robotic technologies and AI research. As it's also a huge conference and symposium for robotic papers and such. Yeah, it's one of the biggest robotics competitions in the world. And going there, you see, and I should have shown. I can show pictures later of us being at the 2018 competition. It was. I wasn't there, Eric wasn't there, but alumni were, and it was very interesting to see the photos. Anyway, there's also some offshoots. So we plan to compete at RoboCup Brazil next month, RoboCup Asia Pacific in Japan, which is November, and then the main RoboCup, which should hopefully be in person, which is in Thailand of June 2022. Yeah, where's my mouse? Our brief history. So we started in 2017. A group of undergrads came together to just form this team because it was a very interesting problem compared to all the other competitions, robotic competitions. And this is sort of in contrast or comparison to like other teams who are usually labs, like have a professor and lab funding for research and are full of graduate students. It's like, yeah, building a humanoid robot involves a lot of challenging design problems compared to like mobile robots. A lot of the algorithms that we have to use, we have to customize because human um, footpath and walking is a lot harder to um, like there's no pre-made algorithms out there because it's very niche. So it's been, yeah, difficult. So yeah, we participated in the 2018 RoboCup in Montreal. We qualified for 2019 and 2020 RoboCup. And just this last summer, we participated in the 2021 virtual RoboCup in the kid size league. We currently have more than 30 active members. Yeah, and we're the only Canadian team to currently participate in this organization. And then yeah, here's Bez checking his corners, figuring out where he is during the competition. Okay, so Bez. So yeah, we call our robot Bez. He's the second iteration. You'll see the first iteration soon. He is 50 centimeters and 2.3 kilograms, so size of a toddler, more or less. He costs $3,800, which might seem like a lot, but when compared to competition, usually it's 3 times the price. So it's quite an engineering feat. And our next iteration is going to be stronger and more expensive. Something to very note is that Bez has 18 degrees of freedom, so he has 18 motors, 18 different actuators that can move all at once. So from every sort of point of view, for mechanical, like figuring out how to make sure we don't break, because since we're 3D printed, we're not as strong as metal, so we got to make sure we don't break our legs as we move, and then also we got to make sure we can do something, movement wise, that actually isn't just random. Okay. Eric.
Oh, yeah, it's my turn. Yeah. So I guess I'll just go through a brief overview of the hardware architecture of the robots. It'll be kind of brief. Yeah. So in this case, we need for the robot to work, we need to have a bunch of sensors and actuators to interact with the real world in this case, right? So we have the IMU, which measured the velocity and angular accelerations and everything related with the robots to give us our orientations and everything. We also have servo motors in this case, which control all the joint movements. And also it gives us all the measurement of the joint movements as well. So all these information need to get processed and compiled together. That's why we have this processor in the middle. It's a STM32 microcontrollers, which will talk to all the sensors and actuators and then process all the information and pass that information into our Jetson TX2, which we use to, run all the software stack. So you can see this chip itself is kind of important, which is what embedded team is in charge of programming. It also uses for free RTOS, which is a real-time operating system on embedded chips, which allow us to enable a lot of the very complex algorithms needed for the information to be processed properly. Next slide, please.
So yeah, something I always like about these hardware architecture, I'll get to it, is how a lot like the human nervous system is, or human body. Anyway.
Yeah, we're building a humanoid robot after all, so it should look like a human. Yeah. Yeah, I guess talking about the Jetson TS2, which we use to drive most of our software stack, as I mentioned before. So as you can see, also interact with embedded chips, as well as also interact with a camera that we have, which is needed for us to process all the visual informations. That includes, like, for example, ball detections, so we can actually locate where the ball is, as well as like locating other robots, as well as the field, so we can know where it is and not run into other people. The Jetson TX also have a dedicated GPU, which enable us to run machine learning algorithms for example, ball detections, which we use. I think we use some algorithm to run the bounding box detections for it. So overall, it's quite useful. Also, we're running Ubuntu 20.04 on it with all the necessary ROS libraries. So if you're working with, I guess, software team, then that's probably going to be your setups. Probably go into that detail later on. Next slide, please. Now in terms of the mechanical team. So mechanical team is mainly in charge of designing and building, I guess, most of the hardware of the robot, the chassis and everything. So in this case, we use Autodesk Fusion 360 to design a robot. It's easy to use, and also it's cloud-based, so it's easier to work together, collaboration together when there's no in-person meetings. I think the earlier design of the I guess the mech designer robot uses aluminum metal bodies, which I guess as fancy as it sounds, it turned out to be a lot of manual labors because we didn't have the proper metal fabrication facilities. So it was very labor intensive, and it was also very inaccurate in many of the details. So that quickly become a pain for us. So in our current design, which is, I guess, BES in this case, we showed earlier, we use this 3D printed parts for easier prototyping and then I guess just easier manufacturing overall. So it's been a quite, I guess, successful design overall, but there's still some trade-offs in this case, which mainly is the strength of the, I guess, the components is much less than the, much weaker than the metal parts. So in our next iteration of robot, we're going to build a combination, build it out of combination of 3D printed parts as well as metal part, just take the benefit from both design. Yeah. Next is the electrical team. So electrical team is in charge of, I guess, doing all the necessary circuitry components needed for the robot to run. We mostly integrate all the electrical components onto a single PCB that we design in-house. So as you can see, this is basically the main design of the PCB. The STM32 chip will also be mounted on here. So yeah, that's everything important related to all the, I guess, the power systems as well as the sensor fusion stuff. Yeah.
Yeah, I mean, we keep on saying STM. Just for reference, think of a better Arduino. That's really all it is.
Yeah, I mean, Arduino uses similar. It's still also like a microcontroller chip, except this one gives us a lot more capability and a lot more powerful. Yeah.
Okay.
Yeah. Yeah, there's also a bunch of like communication protocols that we use. We mainly use UART, which not the best, but sufficient for now. Yeah. Yeah. Guess next slide, please. So some of the current project for Electro team. So one of the major one will be foot pressure sensor. So previously we don't have any foot pressure sensor, so we can't really tell how much pressure I guess we're experiencing on each corner of the foot. That was proven to be somewhat problematic for us to do proper walking behavior. So we decided to add 4 additional pressure sensor on each corner of the foot so that when you walk, you can actually tell like which side has more pressure, so we can make adjustment based on that. So that will be very significant to improving our, I guess, robot behavior overall. There's also this project with PCB manufacturing with like, I guess, with UFT resources, so that we don't have to go to like other companies and do prototyping, which took a lot of time for us previously. Yeah. In terms of embedded team, so embedded team, I guess I mentioned before, is in charge of programming the STM32 chips, which do all the sensor fusion for us. So again, we're using a free RTOS systems, which enable a lot of the, I guess, more complex control loops that we used for, I guess, our sensor communications. This is fairly complex, but I guess just a brief, I guess, overview will be, I think the left and the right part of this diagram basically demonstrate how sensor information is extracted from the sensor and then getting processed by the controller itself, and then getting passed to the our software stuff, and how our software stuff gets sent to the commands get sent to the motors from using this entire, I guess, framework. Yeah, it's called multi-threaded control loop and peripheral management. It's a very long and complex word, but yeah.
Yeah, essentially, it's just like as I said, we have 18 motors. If we
Yeah.
want to walk, we need to make sure that all the motors are moving in sync. And the only way to do that is we need to move them all right. And if you've ever programmed like anything hardware, there's a lot of problems with loops. You might like things just don't work
Yeah.
out a lot of the time.
Yeah, and also in this case, like for a robot to like move properly and balancing properly, right? Like we want all all the information, all the command getting passed within like a certain time frame, right? Like ideally instantly for all the components, so that we don't have to worry about time delay between different feedbacks and stuff, right? So this is where free RTOS came in, which is a real-time system that basically send all the information at once instead of one by one, which is not viable in our case. Yeah. I guess I'll mention some of the embedded projects in progress. So I guess there's overall testing and continuous integration with the existing, I guess, subsystems, as well as there's a project with Ethernet connectivity. So as I mentioned before, our current connection, I guess, main method of communications between all the embedded devices is UART, which even though it's sufficient, it's still, I guess, lacking in terms of speed and bandwidth. So upgrading to an Ethernet connection would be a much better choice in the future. Next slide, please. Yeah. And also some of the current project would be servo motor control. So embedded team also is in charge of controlling the motors, which has its own in-house, I guess, library use for the servo motor to actually move to the ideal positions. There's also a project that we have started, which is a custom servo project. So I think Jonathan mentioned earlier, each of our robot costs around 3 to 4K at least.
Yeah.
Yeah, 90% of the costs are actually in the motors.
Yeah,
So
like
yeah,
because each motor, even though they're so small, like they're like I'm not sure if you can see my mouse, but they're so small, but they cost 250 starting. Whereas a
yeah,
lot of the teams like who have these 12K robots, they're like using 500, maybe $750 motors, or maybe even higher. So it's like,
yeah. So I guess the purpose of this project is to drive the cost down for our motors. So in this case, we will use, I guess, cheaper alternative motors and then break them apart, replacing some of the internal components, and then overvolt it so that it can perform similarly to, a much more expensive motors. So that's the idea for the project. Previously, he's also done the Imu Data Acquisitions, which I guess I mentioned earlier, is in charge of passing all the orientation information for the robots, which is very crucial for it to, I guess, function properly. Next slide, please. Yeah.
control. Okay, so control, you might like, what does the control team do? So essentially, there's 18 degrees of freedom, there's 18 motors that we have to coordinate in such a way that we can walk, actually move, and also make sure we don't fall down. And that's sound like, I don't know, for a human it sounds simple because we can do this all magically, but for other robots it's quite a mathematical physics problem. So like, so according to 18 motors and generate, we're responsible for motion generation for robots walking, so they can walk, get up, kick the ball, dive, and do all sorts of things. We mostly do this through like upper year courses like control systems, of course. And we do this through something called static walking. So we're balanced on each step. So technically we won't go as fast, but we're always balanced so that we can switch. At least that's what we want to do. And then we always being the center of mass is always above the feet. So no long strides. If you think of like when you're running, when you run, you really are going out there. Yeah. And so then we also use PyBoard and Python to mostly do this. We don't use MATLAB anymore. It's really, yeah. And then here's a small video on it.
You'll see that because of the contact, our robot is actually walking along the plane.
Yeah, so that was like done in MATLAB. And notice that's a robot with only a few degrees of freedom. Each leg has 6. So we got to make sure that we give them the proper trajectories. And currently we're working on dynamic walking as well as, I'll show on the next slide. So that make sure that we can adapt even faster. Okay, yeah, next slide. So then next, and I sort of showed some reinforcement learning walking if you were here before it started. You know, reinforcement control system is a hard thing to learn. It's very mathematical in physics. And you usually learn it to the end of your undergrad career or cycle. So we want to think of, why learn control? Technically, we could add reinforcement. We could add more control system into reinforcement learning, but the approach we're taking now is like free form. So we're just giving the reinforcement neural net all complete control of the robot. Yeah. And we're trying to let it figure out how to walk based on certain reward parameters we can do. And with this, we hope it can walk, it can kick, it can be a goalie, and it could pretty much anything. Anything that we've done with algorithms, we think, hey, maybe reinforcement learning can do it better. And sometimes it can. Some experimental data on kicking has shown that our kick can double in length, and that's the same approach with a lot of other teams. The same here. I'm just going to play this again. You can sort of see that compared to if you saw it earlier, it's not falling over anymore. It still kind of is. It's still learning. It has a limp, but one of its legs has actually figured out how to walk properly. Other leg, it's like trading off between speed and stability at this point. But essentially, it has learned how to walk. And so that's the whole thing. Do we want to be more stable, more speed? It really depends. Yeah. And so this is like sort of experiments that we're doing. And we're going to apply reinforcement learning to just general strategy and other stuff. Yeah. So it's like it learns how to do it on its own, and we don't need to learn the math behind it. Though using that with this could make it much better. Anyway, I didn't want that. Okay. So the software team. So this is where, give me a second. The majority of our team is now, just because this is a very big, a lot of work has been done on the other projects, and there's still a lot of work to be done, but software team has a lot of work that needs to be done, and we're getting there. So when we think about humanoid robots, we have to think, how do we behave as humans, And when it really comes down to it is humans are complicated. How we walk, how we know where we are, like our sense of direction, it's like teaching a computer how to do that is very complicated, very hard. And so we have 4 main challenges, which is first computer vision, or seeing the world around us and also making sense of it. Because remember, the computer just sees ones and zeros. We gotta somehow translate those ones and zeros to make actual mathematical sense in some way or form. And 2, localization, or just a fancy word for knowing where exactly we are. Like in a room, like I have a wall close to there. I don't know if I have my camera on, but like, where am I in this room? I'm maybe 20 centimeters away from the wall, and I'm a meter away from there. It's like knowing exactly where you are is incredibly important in order so we can, go through doors properly or navigate properly, which is the next step, navigation. How do we go from point A to point B in the most efficient place without tripping our legs or, going through obstacles? And then strategy. What is our best move? If you think about it, like, I don't know, I'm just spouting about things about life, but it's just like, how should I study? How should I plan? I have a lot of exams and projects, and it's killing me. But I gotta. How many all-nighters do I need to take? It's these sort of situations. That doesn't sound good. And then so these are the main things for software. And then we use tools. We use industry tools that like was it Jason? He's working at a robotics company in Japan, and really, I think he improved their environmental setup from knowing how to do all this robotic stuff here, and he's sort of transferring all that knowledge. So we use ROS, which is Robotic Operating System. It's just a framework to program things. It's the easiest way to say it. It's a bit more complicated than that, but yeah. And then we use C++ and Python. So you'll be learning, if you're first year, you'll be learning that, or you already know it. And we get a lot of experience with that. Then we use a lot of simulation software such as Weebots and Gazebo and PyBullet to generate a very high fidelity software simulation. So when we transfer to real world, it's not too bad, not too far off. Also, yes, this is our GitHub page. We're going to, yep, just start us, check it out, see some things you might like. Okay, so the first half, so I like to break this up into like the four main problems, but really there's two of them that go hand in hand here when I like to talk about it. So it's localization in computer vision. So as I said, with seeing the world around us, there's a lot of information around us. A lot of it is not useful, but there's some that is. And so like so computer vision really, how do we get this the most important part? So if you see on the left, there's a field. I wish I had more visualization, but like in the context of a soccer game, like in the context of like a navigating through your house, how far am I away from the door? And so I'm learning using computer vision to get the depth or the distance from where I am to everything else is. And we can do that in the soccer field where essentially we can use computer vision to like soccer fields have white lines. So we can use computer vision to isolate these white lines and do some math stuff to figure out, okay, so that white line is exactly 5 centimeters or 50 centimeters away from me. And then we get all these dots, like we get all these dots and we put all this information into an algorithm called AMCL or Adaptive Monte Carlo. It sounds complicated, but it's an API. I kind of know how it works. I had to debug a lot of it, but like I just plugged and play. I didn't program it. We do have projects in the future to make our own version of it because it's not very good. But essentially, we take this information of where we are from the computer vision, we put into a probabilistic algorithm that tells me I'm like 90% here. I'm 10% maybe over there. Just to give our best estimate of where we are, because nothing's ever certain in robotics. Yeah. Hope I didn't scare you too much. I just like talking about this. So advanced, and then the next part is advanced robot navigation. Well, pretty much navigation plus strategy as they really go hand in hand. So it's like after we figured out where we are in the field, where the goal is, approximate distance from us, the ball, the enemy players, it's like, it's more of a video game at that point. It's like kind of half video game. Strategy is all about video, like kind of a video game. Both of them can kind of robots are slow. And navigation is really hardcore robotics. So it's like, yeah. So we need to like use this information of our state, of our surroundings. And we need to use this information. That also, we got to also make sure that this information isn't it's probable. So it's like, it could be wrong. A lot of things times are. So we got to figure out what's our best move based on what we can see and what the team can see. Because remember, this is a team-based game of 4 to 6 robots. And in the future, when decades in advance, there'll be 11 robots on the team, which is, I think, is insane to see. Yeah. So what's our best move? Do we want to be defensive, offensive, coordinate a team, like passing, and just like the optimal strategy? The next part is, of course, using motion and path planning to get us there, making sure we don't trip on our legs and that we don't run into obstacles. And also to get us there in the fastest time possible so we can take an advantage. Yep. Yep. So here is a little demo of our current progress in our virtual environment, Weebots. So dynamically, our head rotates and we try to detect the ball. We walk towards it, we line ourselves up, we make sure that we're close to it, we kick it, just like that. It's not a bad kick compared to what we had in the real life, because this is a newer version. Yeah, and then we try to do it all again. We look at our surroundings, we find the ball, we walk towards it, we kick until we essentially get into the goalie, the net. Let's just call it that. And of course, we adjust the angle to kick into the net and avoid other obstacles. Yep. Okay. So I think that's the end of the presentation. And then it's just going to be free from QA. So you can either type it in chat or just turn on your mic and talk. Yeah.
Also,
But
go ahead.
I was just saying, yeah, check out our Facebook page for updates. Also, we have this QR code is for our group. I think a lot of you probably already did that. Did the Google form. Make sure to do it before our first general meeting on Saturday, because this will give you the link to Discord, as well as it'll tell us where to place you within like what you want to do with software embedded in Mech. If you have any questions, just email us and we'll get back to you shortly.
Yeah. I guess I also mentioned since I guess in-person meeting for clubs is still a question mark. So I think for those who are interested in embedded teams, it's most likely that you're probably going to be working with the software team for at least the beginning of the semester. Depends on the situation, because I think working embedded system from home, it's going to be difficult. So we've been doing this for the past year. We're basically just merging embedded team and a software team together for the time being. It might change if we're allowed to go back to campus, but yeah, that's that. I guess that's our current plan for now. Yeah.
I feel like we should be able to go on campus because there was frosh in the pit for the arena in my hall, but it's just, yeah, there's no
Yeah.
confirmation yet. I'm
Yeah.
hoping soon, and I'm hoping at least winter, but yeah, until then, there's still a lot of training that can be done for all the fields actually. But
Oh,
not a lot of hands-on for embedded electrical. Mech can still do a lot of CADing, and I think we're experimenting with ANSI, like simulation software for stress testing our new robot. Yeah. Oh, let's see. Is everyone welcome to the general meeting, or will there only be people that have been accepted for the application? So, oh yeah, everyone is accepted, and so please fill out the form, like the application form, before the 25th. But overall, we do have on-rolling acceptance. If you apply, just we'll try to fit you in and onboard you to your designated team. Yeah, so everyone's welcome for the general meeting on Saturday, September 25th. I didn't put a date on this. It's from 12 p.m. to 3 p.m.
Yeah.
We
And
might
that'll
be
be
changing these times because it's not summer, but and so we had some our timing has been a little bit irregular because of online and summer. Also, we had some, like as I said, mentioned earlier, Jason is in Japan, so we've been doing some stuff to figure out how to work around his schedule because he's like 13 hours ahead of us.
Yeah. We also have two like alumni in
Oh, yeah,
California right
California.
now. So yeah, that's like another 3 hours like ahead of us.
Yeah.
So planning time has been difficult.
Yeah, it's kind of interesting. So we have 4 alumni. Okay, 3 alumni to really help with us on our day-to-day, and then we have a fourth one helping with sponsorship. So it's like, yeah, we have Jason. Should I say the company? I don't think I should say the company. Let's just say robotics in Japan.
Yeah.
And then we have and so he's working as a robotic engineer. Then we have Sharyar working in California, and then he's hardware. And then Nam is working. I actually don't know. I think he's like somewhere between hardware and software.
He does FPGA stuff. I don't know.
Yeah.
Yeah. So yeah, if you decide to join us, you can also like, if you want to talk to them, that's also a good opportunity for you guys to learn more about like, potential future career development and that sort of stuff. Yeah. Again, like we're really open to like, helping new members, can like gain the experience and necessary skills to progress. So yeah.
Something I like to point out, I keep on making this like a showcase, is like it's because when I was the first year, I thought, oh, they would just give me grunt work. They just give me boring work. This is not true. Actually, this past year, we've had some first years working on CNN, so convolutional neural networks. So machine learning for computer vision. I just have to put all those names out. Which is something I'd never even touched neural nets until third year. Again, fourth year. Well, technically fourth year PUI. Yeah, so it's like as long as it's like the more you put in, the more you get out of this. And we try to train you as best as we can. Yeah, and there's a lot of interesting projects to work on.
Mhm. You want to talk about the, I guess, the short-term plan for the competition?
Oh yeah.
Yeah.
So this semester is so okay. We are a little. I mean, just a little bit overloaded for this semester. Because let me just play this out. So we have 3 competitions. We've never done more than one, but because it's virtual, and because we have Jason in Japan, because the Japan competition is actually in person, so we're just going to ship him our robot. So we have to do a bunch of revisions and make sure our robot's better than what it was in the summer, because we want to add dynamic walking, reinforcement learning kick, and maybe a goalie and some other stuff. You know, which is really padded in. See how they fare well in a competition setting. So that's going to take us middle of October. Then we have to build our second robot, and then test it and make sure our walking engine is tuned for it. And that's before the end of November.
Mm.
And then around that time, December, I'm not sure when, but we have to redo our paper and then refilm a qualification thing for the June, like the Thailand, the real Robo Cup, because they always
Yeah.
have December deadlines.
So what RoboCut does is that it has regional, and then you have like I guess, the kind of worldwide competition every year. So we've never been to some of the regional competitions. This is our first time attending. And the worldwide competition usually held in summer every year. So in this case will be Thailand. So yeah.
And we're hoping it's in person though. And there might be a championship league because of like the last year, like summer was virtual and it was pretty easy to run from what it seemed. So there
Mm.
might be championship league where in the middle of the night we have to commentate because most of the teams are
Oh yeah.
European.
Yeah.
Um, as our team plays against another team, it's a lot of possibilities.
Well, it's also pretty fun because it's like, they actually stream the games once they like actually like render and compile everything. They will actually like stream the game on Twitch. So it's like, kind of interesting to watch. Yeah.
You're just
Mm.
getting some photos. Um, yeah, I'm wondering what we better go through some of these photos, or I mean, if anyone has questions about anything, of course ask. But I'm just trying to feel this awkward silence. What would be better? Go through old photos, or maybe watch the final match?
I want to watch the demo video over like from start to finish because we should only show like a few seconds of it, right?
Demo?
For the
No, we show
kickoff.
like the full demo video. What do you? Oh,
Did
you
we?
mean this demo? I mean,
Yeah,
it's
yeah,
the
yeah.
same thing. For 5-6 minutes.
I mean,
I
I
had
actually show it.
2016. It just tries to short do this goal.
Yeah. Okay.
How do you coordinate with other robots on your team at the competition? So our goal, oh yeah, our whole goal is to be a team by ourselves. So if you have 4 robots, you just need 4 robots to play as a whole team. Otherwise, since we only have 1 robot right now, we can pair up with other teams because there's many teams who don't have 4 robots. They're kind of expensive.
Mm.
So usually there's a standard framework because it's all through there's like they have their own network. So we send like I don't know what the term is. We
Yeah.
send
So basically, they have like a server, I guess, a server-ish thing running
yeah.
through Wi-Fi. So that's how each team each robot can make with each other. So it's basically sending and passing information to that server.
Yeah, I
Um,
think it's like we send it to that server and that server sends it to all the robots.
yeah.
And so usually there's a common framework on how to, how that some teams have developed on how to communicate to make sure that all the variables in the right area.
Yeah.
something. Yeah, I guess I kind of want to play the final match because it's very interesting. Okay, can you see it?
Yeah, I can see it. Yeah.
Yep, see it, and it's very. So the blue team is Starkey, which is a Russian team. Also, MRL is actually walking backwards. And then MRL is Israel. Oh, yeah, I believe. Oh yeah, will there be opportunities to learn how to use ROS/MATLAB for working with software? So we used to do ROS and MATLAB until it's not very good for software practices since it's very closed off. It's a lot of bugs. Um, So we used to do MATLAB. If you want to do ROS and MATLAB, we can definitely talk to us about learning that. But right now we just do ROS, Python, mostly Python with some C++. So it's easier for like computer vision. We usually use C++ because it's more computationally heavy.
Yeah, so we mostly face off MATLAB just because it's like an extra layer stuff you have to jump through, and it just not efficient in keeping everything like separated. Yeah.
So this is like start the course. So it's already 2-0. So first, I think I actually don't know. So they have to. There's a lot of like in a game. There's a lot of rules, or you get penalized, and then you get red carded, and your robot gets taken away. So that's MRL, and they have the best kick. That's a 2-meter kick, more or less.
Mm-hmm.
Let's see, since they don't have obstacle detection, and actually a lot of teams don't have obstacle detection. And we're actually one of the few, and we actually saw it working thing. Because a lot of these teams just keep on running into each other, and then they get penalized, and then they just kicked it too. Yeah, so in a game, there's a lot of different penalties, and you have to program for strategy, how it should respond. It's usually just to get away from the other robot, because yeah, I like that. If it's a penalty and they think we did something wrong, then yep, we get penalized and get sent out. At least this is how it is virtually. In real world, it's a lot more lenient because it's people doing this. Yeah, but so like our goal or our dream is to build robots as strong and as fast as this, and to get team communication working. Once we have the second robot built, I would. What are the areas of software that are better that use C++? So right now, we've been phasing out a lot of C++ just because Python is so much easier to train and you work with and also just experiment and test with. But right now we have computer vision. So everything we do with OpenCV. So how we detect the lines, like the soccer field lines, and also get rid. So another thing we have to do is why did it stop? Okay. Another thing that we have to do in computer vision is make sure that we're not seeing above the green line, because there's a lot of noise. Like these are matches played in real life. So if we're seeing things not on the green field, then it could be a problem. So we want to draw a line around that. So we do this for like contours and like just removing things. So most of that's in C++ because it needs to be computationally fast and efficient. For embedded, pretty much all of embedded is in C. And C, I don't even know if it's used C++. I actually don't. I think all of it, like including using FreeRTOS, is just C++, just C. That was pretty much just like it's like programming Arduino, but just more complicated.
Just more okay, yeah, sure.
I think you can even use the Arduino IDE.
I mean, IDE is just IDE, right? So that
Yeah, but
it's more like how do you actually like compile and run it, and
So see that's very interesting. Where like they see the ball, they see it's about to go in, and they try to, even though that's not the goalie, because that but they got in the way of it. Seeing some very interesting behavior. Oh, and then Something to note about this too is, since these are humanoid robots, and also we want them to be as human as possible, there's a lot of sensors that robots can have. That would make this a lot easier. Like if you know of Connect and lidars and like point sensors, like they can get distance very easily. But we can't do any of that because the humans can't do that. So we have to define other ways, and it's very like because I'm taking this. Eric and I are taking this class on computer vision, and we have to do it where because it's very interesting. I've always loved it because this is a part of the code I worked on for computers for the camera system. It's very interesting where you find like a pixel on your like 2D image, and you got to figure out where is that in the real world and in the 3D world, real world. And you got to do a lot of projections, linear algebra.
Linear algebra.
Oh god, it's I mean, I say projection, but it's a little bit more complicated than just your regular projection. You ray trace it to the world, and it's interesting. It's fun.
Yeah. There's also a team that use like two cameras that allows them to do depth perceptions, which is
like
also
StarKit.
useful. Yeah, StarKit, yeah. But they also require a lot of processing power, so we're only using one at the moment.
Yeah.
Yeah.
Actually, most teams only use one because it's like, yeah, the stereo would be better, but it's just there's a limited bandwidth that you're allowed to use, like especially in simulation. So I don't think it would actually matter for us too much because we use a 640 by 480, but then we scale that down to 100, I think 200 by 100 or something like that, because that's what our neural net inputs for some reason. I don't know why Nam decided that, but he did.
Just to make it fast, I assume.
I'm assuming to just make it faster, but it's just an arbitrary number, I think. You just kicked his shin. So yeah, this is what we want to aspire to. Though there are a lot of teams who just couldn't play. Like some yeah. It was great to
Yeah, go ahead.
I was like, it was great to play because we actually got to play against StarKit in our bracket, the world champ, because StarKit blue team wins in this game. And so we got to play against the world champion. And we got destroyed, but it was very fun. You were saying, Eric?
Oh, I was just saying, like a lot of people like getting in this thing to work with the simulated environment is actually kind of difficult. A lot of team couldn't get their robots to like move at all. There's one team that just like fallen over and they're just like slowly drifting out of the field for some reason. Like mystery, yeah.
To give out like how hard simulation all this stuff is, it's just so usually there's 20, maybe 30. Usually it's been 20 teams that sign up for this, 20 to 25, I think. But only 12 actually made it. Like, I don't say made it, but they actually went to this virtual competition. There was supposed to be a 13th, but they couldn't get their robot simulation to work. And then in the quarterfinals, where you think they got rid of a lot of the robots, two of the matches had a side, had one side where they weren't moving.
Yeah. There's like a lot of integrations that the software system need to do, right? Because you have all these systems, all the strategy stuff, all the localization stuff, all the motion planning stuff, and those stuff need to be integrated all together, which make it like a fairly complex problem. Yeah. So a lot of places could go wrong in the competition.
Especially like in real competition. Same way it's so nice because in real competition, it's so easy to break everything.
Oh yeah, in real competition, you also have to face like mechanical parts breaking, right?
Let's see. What else do I want to show?
I guess we can show some of the photos, I guess.
Yeah. What is
this? It was
this?
like 2017, 2018, so that's like...
This is like 3 degrees. This is a very early mock-up. Oh, wow.
Yeah, so I think assuming this is like first iteration, right?
Yeah.
Yeah.
this. Building
Yeah.
aluminum parts by hand. So
Yeah. If you ever try to cut like stainless steel or metal by hand, it's a pain.
here's like pictures of the first iteration robot of the the first leg.
Mm. Honestly, I'm surprised how well they cut it. Because I remember first year when I was cutting stainless steel, it was like looks like a dog bite off the edge or something.
Be off a little bit because this is going this way. These ones have network. These ones have network.
Oh yeah, of course. There's a lot of when initially building the robot, there's probably a lot of just, oh, these motors aren't working. I don't know why. Yeah, testing the initial walk. Actually, something that's very interesting about this first iteration of robot, and also why we kind of went away from aluminum, was we were using weaker motors because they were cheap. And there's a reason why they're cheap. And we had to when we were making the qualification thing, we had to kind of gut it. And so there was like no onboard computer. It was all like through wires. It's interesting. Yeah, so here are actually from the competition. So you see like these are, I think, teen size robots. So they're like the actual size of people at this point versus our like toddler baby size.
This is 2018 at Montreal.
I believe so. Yep.
Yeah.
And it's like just looking at it, insane in person. Oh, and yeah, this is a different league because RoboCup has a lot of different leagues for soccer. So this is like if mobile robots are doing it, and they can kick it and they can.
Yeah, those are fast. It's like they
Oh,
don't
they're
have
very
to
fast.
walk. They just have like wheels at the bottom, so they kind of walk. They can like run very fast. Yeah.
Right. Then there's like because there's a bunch of different leagues. This is called Industrial League where they have to solve industrial problems. So it's a mobile robot with a KUKA arm on top of it, and it just has to like probably grab something or fix things.
Hmm.
Oh yes, this is a like this. This is the size of that guy. It's just this is a full humanoid robot, and the the goal of this whole project is to make 11 of those. Well, I mean, the competition in total.
Hmm. It was like almost adult league.
This is adult league. This
Oh,
is
is that adult? Yeah.
yeah. It's just like it's kind of candy seeing robots the size of humans at that point.
Hmm.
All right, this is our team. So this is Jason, that's Sharier, and this is Nam. They were at the competition. They just traveled.
Hmm.
Yeah, Sharier. Trying to figure out what's wrong with the robot, calibration. Something about competition that's kind of sucks is always the calibration. Simulation's so nice. It just usually works. Actually, a lot of times it doesn't work. But then when it does, it works. And then in real life, you try the same thing. It's just like, it should work. It's not working. And there's some sort of calibration error.
Yeah, competition is stressful just because there's the deadlines and stuff suddenly doesn't work and it gets stressful. When the last time for our virtual competition, Jonathan hadn't slept in how many days?
I didn't sleep for 4 days.
Yeah.
I mean, I had some sleep.
Yeah. Just to get things to work. Yeah.
And then trying to figure out at the competition, they were trying to figure out the trajectories because it wasn't exactly easy to make.
Okay, I think I need to. I
He's just trying to get us, right?
Yeah.
Stop. Filming.
Yeah. At the same time, if there's anyone has any questions or things.
Okay, I think I need to. I need to run it on.
I think it's the same video. I think it's just looping.
Yeah, it's the same. Yeah.
Stop. Filming.
Yeah, that's looping. Yes, well, I think in that competition, I think we managed to get the robot to like do what? What did it do again? I don't remember exactly. So it did some stuff, trying to like do get ups and stuff. Yeah.
Yeah, it was able to get up front, get up back.
Yeah, but it wasn't able to walk. I think.
Yeah, it was able to walk, I think. What was that?
Oh, got it. Oh. Do not stand that first, but it's fine.
Close, close.
Simulation stuff.
So the old gazebo simulation.
It's like each motor has its own thing. Then here's photos from, yeah, the last non-COVID year, I think.
Mm-hmm. And we also got a server in my hall that would run some of our machine learning,
Yeah,
learning stuff, which was quite useful.
I think it's like testing some walking engine stuff. Oh, slow motion. Yeah, I think they were trying to figure out the gait of the walking. It's very interesting to see in slow motion how it balances, how it absorbs the impact, how it walks, and it okay.
It's like teaching a toddler how to walk.
Well, so it looks like we're just down to 6 people left. Good is. Yeah, I think we were just trickling out during this. Because like the presentation's over. If you have questions, you can ask questions. I'm okay with people leaving.
Mm-hmm.
Oh my god.
Okay, we're just down to last one.
I guess we can just call it a meeting then.
Yeah, I should
Yeah.
have called it earlier, but like I just that's fine. I
No,
should
it's
have done
fine.
that.
Just chatting. Yeah.
Yeah. Yeah. Any questions? You're Chris's brother, right? I just checking for your name.
Hey, yes,
Oh,
that's
yeah.
me.
Hello.
Hello.
Hello. Are you Jonathan?
Yep.
That's crazy. I can see your name tag. It looks interesting.
Yeah. Just tons of things to do. Lots of
Are you,
projects.
yeah. Were you an Eng side?
Yeah. We're both Engine.
Yeah,
We're both.
Oh, nice. Okay,
Mhm.
cool.
Yeah. You're a second year, right?
Yeah.
Yeah. You think of Robo?
Yeah. An option. Don't know yet. Still have time.
Yeah. Because I thought it'd be Robo, and then I said, hey, maybe machine learning's cool. And it's like then
Yeah,
I
that's kind of, yeah.
and I chose that. And I was like, no, I want Robo. It's like, oh.
Yeah, I heard last
People
year
say like the AI minor doesn't have like it's, you can do a lot of the AI stuff in the Robo one.
I mean, like,
Apparently. I don't know,
Robo, Robo, ECE, and ML. It's like, yeah, so you get a lot of choices, and the electives you can pretty much take like a lot of the same classes. I like Robo because there's a lot of robotics classes that are really just made for Robo.
Yeah. So is